Welcome you all for my presentation, and this is fire structure interaction that is dealing concrete wall under a fire load. And again, once again I thank my wife, because of her I am here. And this is a collaborative work between two chairs, fluid dynamics and the structural analysis, and I come from the chair of fluid dynamics, so I can show you some colorful plots, I guess. And yeah. As a next step, we can see the outline of the presentation that I am going to give. So at first, as always, the motivation, and second, I will briefly introduce you to the fluid dynamics or fire dynamics, and the structural solver, and then the coupled simulation of fire and structure, and finally conclusion. So before we begin, we all know fire. So fire is, in my perspective, fire is more dangerous and destructive in nature, and it can occur anywhere. Like we have been hearing a lot of news about the forest fire and a lot of building fires, but today we will be focusing only on the building fire and its effects. And so these are some of the effects that one can address or one can get when a fire is occurring in a building. So the most things that is interest in this presentation are the smoke, ash, particulates, damage. These two are the most important things that we are addressing with the current project. And here I will be talking more about the damage that it is dealt to the structure. So we will be speaking more about the structural damage. So this is really a tragic real incident that occurred at London, Grenfell Tower. So here on the right hand side, on the left hand side, you can see that the firefighters are trying to extinguish the fire that started, and they nearly took approximately 60 hours to completely extinguish the fire. So the fire is that much dangerous. And on the right hand side, on the left hand side, you can see the progression of fire from a single apartment to 106 apartments over time. And on top of it, you can see when exactly the fire started, and the next timelines are from that point or from that time in over 7 minutes and 22 minutes how the fire is being progressed inside the building. And at the end, more than 3 hours later, it was completely engulfed with fire, and we lost 70 good people on that day. And you can also use this QR code to see or to learn more about fire that is occur or that is outbreak in a building. So this is the aftermath of the fire. Still there is fire, but you can already see a huge concentration of smoke that is coming out of the buildings, and also the structure already damaged. So this puts the firefighters and also the people who are already inside the building to be evacuated, or for the firefighters to rescue the other people. It is not an easy thing, or it is not an ideal thing to look for. So this lets us in the position to understand, or it makes a necessity to understand the fire behavior and its impact on structure. So our goal is to build a robust fire model that gives the firefighters a basic layout of the understanding where exactly the structure is stable and where we can expect fall, and it also at the end will lead to a stronger building codes. And on the pictures you can see these are all experimental studies that are meant with fire, and you can see the columns are ruptured, and we call this with the word called spalling. I will also come to that word later, but you can see the effect of fire or thermal load on the structure. So next we move on to the fire dynamics simulations. So at first I will try to explain a basic view of physics that is involved in a fire. So fire is a combination of physical and chemical phenomena. How does a fire occur? Fire is a chemical reaction between a fuel and oxygen that is in the surrounding. So when this is the chemical reaction, is when this chemical reaction is occurring, we get a lot of byproducts and also a release of toxic gases and huge amount of heat energy. And in addition to that, to model a fire or to simulate a fire, we need heat transfer, fluid flow solver, and also to track the smoke and other toxic gases that are produced as a result of a chemical reaction. And on top to that, we also need to model combustion, and also there is a submodel for creating this fuel from a solid. So all comprises, and we get a fire simulation as a multi-physics problem. And here you can see this is a typical example where we have a solid fuel, and when the solid fuel is subjected to a huge amount of heat, it undergoes pyrolysis, which is a separate submodel, and due to the pyrolysis we have a release of fuel into the system, and this fuel, it interacts with the oxygen present in the room, and then it undergoes combustion, and this is again a separate submodel. And due to the combustion, as a result we get the radiation as a heat energy that is released from the fire, and also we have smoke propagation and convection. In addition to that, we also have turbulence model. So all these submodels comprises our simple fire simulation. And for fire simulation, we use Fire Dynamics Simulator, which is a US based open source code developed by NIST of USA, and these are all some of the simulation parameters that I use for a general fire simulation. And the fire simulation, they already have the heat transfer equations, but it is limited to only the heat transfer in 1D direction, and it is limited to only the heat transfer. It doesn't address the extra model that we need, like a crack in the concrete or a hole in a concrete. So that's the reason that we are trying with the external structural solver combined with preCICE. So now let's always stick to the basic example, very simple example. So this is a nice room with a fire source at the corner, and we have window and a door. The door leads to a beautiful balcony, and here you can see the dimension doesn't matter, but still I added it. And the material concrete is taken from the Eurocode, and we have an ambient temperature of 20 degrees Celsius, and we specify fire source in terms of heat release rate per unit area. This is nothing but we specify this one in such a way that this value represents how much amount of fuel is released into the system, and this value is coming from various experimental data, and for specific conditions like a hotel room or a room from a house, we have different values, and that value is 250 kilowatt per meter square, and we use propane as a fuel, and combined with the soot yield and CO, carbon monoxide yield. Soot is nothing but the smoke here. So on the left hand side you can see at first the development of fire along with a little bit of smoke, and you can already see that the smoke is escaping through the door and the window to the atmosphere. And down to the left we can see the development of fire over time. So at 160 seconds, because of the current configuration of fire, we can see that already it is obstructing the view, and the smoke is so thick. The smoke is nothing but a hot layer. It also adds the temperature of the room to a higher value. And let's make a slide more colorful with the animation. So the animation that I have is the temperature distribution that is just near to the wall, and also you can see smoke. So here you can see the temperature distribution near to the fire is higher, and even after some time you can see the temperature is maintained at in the green level, maybe around 150 degrees Celsius. It's because of the smoke, because the smoke is a hot gas. And moving on to the next part, we have our concrete structure or structure simulation. So before I go into the structure simulation, let me explain or give a brief introduction or quick introduction about what a spalling is. What a spalling is and how does it occur, why does it occur. So when a wall is exposed to the fire load like it is here, So due to the fire load, the water vapor inside the concrete wall and the chemically bound water vapor escape in both directions. So the water vapor that is escaping towards the wall or inside the wall, after some point due to the temperature, large temperature gradient, it condenses and creates a moisture clog, and this moisture clog increases the pore pressure, which increases the thermal pressure as well, and as a result we get a chunk of material that falls down from the concrete structure. So this process we call it as a spalling. And so at moment we are using the first theory, differential thermal gradient, for creating a simplified model, as our idea was coupling the fire solver and the structural solver. Later we will move to the more complicated theory 2. So these are all the simulation parameters that we use for the structural simulation. And yeah, so recently we got liking to a paper from Pimienta, and we thought, hey, we can use this wall condition or this wall, and in a hope that we can get our simulation data and finally compare it and validate our model at the end. So we have what we have is a simple wall of 3 meter high and 1.2 meter breadth and 0.2 meter thick. And we have different configurations of it, but we are only using the concrete model at the time being. We are not using any reinforced steel inside it, and we don't apply any load on top and bottom. And this is the simulation of the structural solver, and here we apply a thermal boundary condition from ISO temperature curve, not the temperature from the fire simulation, but ISO temperature curve. And here you can see how the temperature is distributing in the middle plane of the wall, and you can also see the nearing points of the wall are clouded with high density mesh, which means we have more mesh inside this smaller thickness than we have it in the middle. So we can capture the transfer of temperature or the distribution of temperature clearly, and within a certain time, I think it is 30 minutes, we can see that in 2 centimeter we have a high temperature gradient of about 500 degrees Celsius. And finally we move to the coupled fire structure simulation. And at first, so I know it is still the same, yeah, it's just the same thing that was taken from the preCICE website, maybe even older. So I don't think so I need to explain it to everyone, because you all might know already what this is. So this is new. So we have FTS and THM solver. I also changed the color to look it new. And lastly, not lastly, but nextly, we move to the flow chart of our complete coupling scheme. And I am not going to speak about the solvers in detail. I don't want to bore you. I just want to give you a brief structure of how our coupling scheme looks. So it will start with FTS, which is fire simulation. We basically give the input, the fire solver solves for the temperature, and then he gives it to the preCICE. preCICE gives it to the structural solver, and structural solver solves it for the thickness of the hole, or the spalling thickness we call, but in general it is the depth, how depth the hole is being created. So this depth, if it is greater than 0 meter, then he will write it to FTS. If it is not, he will loop until he gets the next temperature data, and then he gets the non-zero spall thickness. Once he writes the spall thickness to the FDS, and preCICE gets it and he gives it back to the fire solver, and the fire solver, he has separately implemented subroutine that checks for the thickness, and if it is if there is a positive thickness, then it will create a hole in the wall or on the wall, and then this will happen during the runtime of the simulation. It won't stop the simulation. It will just as a process that is inside this simulation time loop. and then finally when the time conditions met, the simulations end. And for the preCICE, we use serial explicit coupling scheme, and we use first participant method, and we also use the nearest neighbor data mapping. So again we go to the very simple test case. We have a room with a wall that is separating the room into two segments, and on one segment we have a fire, and here you can see the fire is in front of the surface, so which means we are seeing it in this direction. So this is the front surface, the surface that is exposed to fire, and after a certain time we will get some cracks because of the fire load, and when during the starting time itself the temperature is already being transferred to the structural solver through preCICE, and once the preCICE finds the location and the depth of the spall, then he will send it back to the fire solver, so the fire solver can create the hole or the crack in the wall itself. So this is again my test case. So here we can see that the wall, the fire source, and the A, B, C, these are all open to atmosphere. I am not restricting any smoke inside the room, so the smoke will go out. And these properties, the floor properties, the concrete properties, again it comes from the concrete structure, Eurocode of the concrete. Again we use propane, and we use here a higher heat release rate per unit area. It's because we are testing, so we just want to give it a higher value so that we get the results faster and maybe even better visualization. So here I added also the chemical reaction that is happening for a propane that is combined with air, and then you see the byproducts and the heat release rate. So yeah, and next, so this one, this is a test case, preliminary test case that is still running, and here you can see the on the left side it is the temperature data that is from the post-processor of Fire's FDS, and here it is the transfer data that we get from the structural solver. Here we can see that the exchange is good, and we got we got what we wanted. And next, this is the colorful thing represents the hole that is made because of the high temperature. The spall thickness is created, and it is received from the structural solver to the fire solver, and over time, of course, we made the structural solver a little bit weaker in purpose to get to this result, because in general it will take a longer time. So you can see the development of hole over time, and finally you can see for 1000 seconds the complete wall that is exposed to the fire or above the fire is completely filled with holes. So this is just the first layer of the concrete is falling down, but for the complete hole to penetrate the complete wall, it will take even larger time. And I added a spontaneous slide. So this will somehow explain. So this is from the dummy solver, it's not from the actual structural solver. So this we have two rooms, room 1 and room 2 separated by a ceiling, and over the time the fire accumulates the smoke, and because of the increase in temperature on the ceiling, over time you can also see that the hole is being created as a part by part, and after 70 seconds the hole is completely created, and you can see the first escape of smoke to the next room, and in 100 seconds it's completely again filled with smoke. So smoke being the hot gas, once it engulfs the room, it activates other sofa kind of material to cause fire again. So it will extend the fire even to all the neighboring rooms. So finally we come to the conclusion. and outlook. So first I will give you the conclusion. So the transfer of temperature data from fire to structural solver is done, and the location and depth of multiple cracks from structural solver to the fire solver is also done. And we have working preliminary two-way fire structure coupled model. And the future steps would be, as I said, this is only a concrete wall, but we also would like to change the material properties of the wall and also add reinforcement to the wall. And also we would like to examine, or we would like to extend the coupling to a progressive collapse of the wall. So that will be our future steps. So at the moment we have this orange box. So what we have future plans are, so we will be coupling it with Abacus. So the Abacus does the macro modeling, and it gives us the progressive collapse. So it is again connected to the FTS for the if it need to decide if the wall has to stand or if the wall has to completely come down. So I take this moment to acknowledge and thank our financial partners. And finally, I conclude my presentation with a thank you for your attention.
Thanks.
I have a question about when you say you are computing the cracks. Are you doing this as a damage model, or?
Yes.
Okay, and then
So
when you reach a certain threshold, then you break off a grid cell, or do you compute which volume is affected and then?
So it is a damage model. So it's he is doing phase fracture modeling.
Yeah.
So I also heard it
Phase
from your
shield
talk.
fracture, yeah.
So he is doing that. So he basically gives the location and how. So the location already determines which position of the wall is going to be cracked, and also with the depth I can see if it is greater than a single grid element, then of course it will be done. But if it is less than a single grid element, then it will wait till it reaches one grid element and then it removes grid by grid.
Okay. And then you also change your geometry.
Yes.
Okay. Thank you.
Thank you. Just a question, do you take into account conductivity of the solid at all in terms of thermals? Because I noticed the two-way coupling is more like damage back to the fluid solver, but I could just imagine that you actually also have thermal conductivity along the wall as well as your temperature dissipates through. And I'm sure you know more, as the water is being pushed in and out, that would also probably change the thermal conductivity of the wall.
Yes,
as
true.
you're going through, so I can see a number of challenges there.
So as I said, these are preliminary results, but we also look for the thermal conductivity. As you said, it as like I showed the temperature distribution in the structural solver. He also looks for the thermal conductivity on the wall, on the surface of the wall, and along the depth of the wall. And this, at first we started with 1D structural solver, but we faced a lot of shortcomings, so we directly switched to the 3D structural wall. So the structural solver that I showed you, it's a 3D structural solver. Okay. So it takes care of also the thermal conductivity.
Okay. And sorry, maybe I can just do you also ever send the heat flux back into the fluid, or is
no, we are not sending any heat flux from the solid, because whatever the structural solver solves, it solves for itself, and it only delivers the damage and the depth of the damage.
Okay, very interesting. Thank you.
Thank you.
Another question there. When spalling happens, the concrete falls down on the floor, right? So are you, or do you plan to look into the effect that would have on fire suppression? Let's say one of the example you showed that the roof completely collapses and the smoke escapes to the other room. So in that case, if the roof is completely coming down, that would have some suppression effect on the fire that's there in downstairs, right?
Yes.
Can that be coupled back to the fire source?
So our idea is when, as you said, when it is completely collapsed, then we call it as progressive collapse, and of course we are going to take care of it in the future. So when it is completely collapsing, then we won't be having any structure at all there. And of course, due to the impact, the fire source at the bottom would be completely gone, but not the smoke. As I said, the smoke, it can go up to 1200 degrees Celsius, which means it can lead other parameters, like it can lead other materials to cause or to undergo pyrolysis. For example, the wooden table or the sofa, so they act as a next fire source if it is something that is undamaged. So as I showed you in the first slide of the Grenfell Tower, so it will take some time for the fire to develop, but once it is completely developed, it doesn't matter if it is a progressive collapse or if it is a minor collapse, it will be very hard to extinguish.
Okay, so it'll have the falling debris will have very minor effect on fire suppression.
Yes.
Thank you.
So right now your coupling interface is really like is one plane, right?
Yeah.
So actually when you have the spalling, you would need to change the coupling interface eventually as well, right?
Yes, that is actually a challenging task because we are, so at the moment if I have 100 cells on the wall, then if the spalling is occurred, then it has one more cell, right? So we are already I have already taken care of that, that it includes or it adds to the array that I am sending, but I think it is not well received on the other end, because it completely collapses the domain or so he takes the array and applies it as a boundary condition to the structural solver, and that one it is causing a lot of problems. So at the moment we only pass the surface, so we are not worried about, at the moment we are not worried about the newly created ones. So because he gets the surface, and still even though I am removing it from the fire solver, so we still have the position, and still that position is computing the temperature of the solid wall, surface temperature, and he is still sending that temperature to the structural solver. The structural solver on the other hand, it takes that temperature, and if it has already a certain thickness of depth or certain thickness, he will compute with the temperature if the thickness is growing. So he will give me back the newly updated or newly extended thickness, and my fire solver creates even or extends the hole.
Would the fire solver be able to extend the domain? So at some point you have to extend your fluid domain if more and more of the wall cracks down, right?
Yes. So if I understood, actually I didn't understand quite clearly. So extend in the sense, or domain extension in the sense.
Well, right now your fluid domain is kind of the complete room,
yes,
right? And if more of that wall
yes,
cracks down, then your room is getting a little bit bigger.
Yes.
Right. So can the fluid solver
yes,
handle this?
Yes.
Yeah.
So this is a typical example for that, because so this may look as a single hole or a simple hole, yeah, but at the moment before the simulation starts, it's a completely solid, and the fluid solver doesn't know that it is a fluid domain. So once the hole is started to create, and he understands, or he's given a fluid domain properties, so he will start acting as a fluid domain. So that's the best example is the propagation of smoke. So because it is a fluid domain, the smoke is propagating to the next room, or else it would stuck in the below the structure itself, even though I changed the geometry.
Yeah. So where I want to go with this is I think it could be really an interesting test case for Frederick and the remeshing.
Yeah, that's why I actually asked you some questions about remeshing, but I didn't follow it up. But I just started. I just put the initial thing, so you remember my name and face.
Yeah. You two talk at the poster. Yeah. Could also be interesting to then maybe the next wall to switch this on after some time, right?
Yeah.
And then you would need a similar feature. Yeah. All right. Then I think we are ready for lunch. So thanks again.